this lecture right now, and it's going to pick up the audio. You can see it picking that up, and then it's sharing the screen. So anything I bring up on the screen, it's going to show us, and it'll record this. And I left off on problem number 41. This is where we left off yesterday, right? Okay, so let's take a look at that one. We noticed that this was a trinomial in quadratic form. So we can tell that because if you take the variable part of the middle term and square it, you get the variable part of the first term. Okay, if you're looking at exponents, you could look at it this way. If you take this exponent and take half of it, you get that exponent right there. Now that works if there are exponents. If there aren't exponents, that doesn't work very well. Okay, so it's better to just say, take the variable part of that middle term. If you square it, do you get that variable part of the first term? In this case, we do. So that was our u. Our u is x squared. So wherever there's an x squared, we put a u. So that's why this says 4u. There's the minus 5 and the equals 0. And then right here we had x to the fourth. Well, that's what you get when you square x squared. So there's our u squared. So this is a u substitution. This is where we left off. And if you factor this, we're looking for two numbers that multiply to be -5 and combine to be +4. So what does that? Does this factor? It does. What numbers? +5 and -1. Which means we can write down the answers. This would be u equals -5 here and u equals +1 there, right? Now we'd be done here if the problem were about u's, right? It's not about u's, it's about what variable? It's about x. So we use this little formula right here again to reverse the substitution to change them back to x's. So this is going to be x squared equals -5 and this is x squared equals 1. And about this point, you're looking at one of these and you're saying, there's something that doesn't quite look right about that. Which one is it?
X squared equals -5.
Yeah, it's the one with the negative, right? Because when you square something, you get a positive, and it's saying a positive equals a negative. Does that ever happen? It doesn't, okay? There are no real solutions from that one right there, so we can just cross that off. Now, when I solve this one, I need to take a square root, right? And we mentioned this yesterday. If you put a square root in a problem, what else do you have to put in there? You got to put a plus or minus. So the answers on this one are plus or minus 1. Okay, now if we were counting imaginary answers, which we'll get to at some point in this class, that would be them. But we don't have to worry about that right now. Remember, from 1010, it is possible to find a square root of a negative number. Imaginary numbers get introduced there. Everybody good with that? Okay. I'm going to change the problem just slightly. What if it worked out to be this? Let's say the problem had been x to the fourth plus 4x squared minus 7 equals 0. Yeah. Very good. Okay. And before we do that, we're going to say u equals x squared. This would be u squared plus 4u minus 7 equals 0. And Josh, say that louder. Say it again. We're going to use the quadratic formula. Can you tell us why?
Because no factors can add up to 4.
Yep. We're not going to find any factors of 7. We're not going to find anything that multiplies to be -7 and combines to be +4. Won't work. Okay? So if that's the case, we're going to solve this using the quadratic formula. So that's, remember I asked you to make sure you had that memorized. So this is going to be u equals -b plus or minus big square root. Go ahead and sing it if you want. 16 minus 4 times a times c. Please don't mess up this part right here. So there's the b squared. Minus 4 times a, that's a 1. And c, that's a -7. And then all of subtracting something. We're going to be adding, right? Because it's a negative times a negative. So we're going to be adding 28. So here's what we've got. U equals -4 plus or minus big square root. 16 plus 28 is 44 all over 2. Let's simplify a little bit more. We can write this as -4 plus or minus. Let's see, that would be 2 times 2 times 11. So 2 radical 11 all over 2. And then we notice that we can simplify this a little bit more. There's a 2 in everything here. So this is going to be u equals -2 plus or minus radical 11. Now in 1010, sometimes you wrote these as two separate pieces, so let's go ahead and do that here. One of them is u equals negative 2 plus radical 11, and the other one is u equals negative 2 minus radical 11. Those are the two answers. Are we done with this problem, though? No. Because this is the answer in terms of u. We want it in terms of x. So this is where we have to take and reverse that substitution. Whoops. Radical 11. And then this is going to be x squared negative 2 minus radical 11. Now, take a good look here. Hopefully, to this point, it wasn't very difficult. What do we do now? If you want x all by itself, what do you do now? How do you get rid of squaring? Take the square root. So I'm going to have to take the square root of this side and the square root of this side. These are pretty ugly, but you can type them into your calculator and get a decimal approximation. Is there anything wrong with this right here? Other than it's really ugly looking? You can. It's not very nice, but you can still have that. Yeah?
It's a negative.
It's a negative. If you take negative 2 and subtract radical 11, it's going to be negative. Can we take the square root of a negative and get a real number? No. So there are no answers that come from here. You don't have to worry about any of those. So your answers on this one are going to be plus or minus square root negative 2 plus radical 11. Now that's an exact answer. You can type this into your calculator and it'll spit out a decimal. But remember, one of them is going to be positive and one of them is going to be negative. Okay? Any questions? Who's done with 1.4? Totally done with 1.4. Fabulous. Okay. All right. Go ahead and put that away. If you're in my class, I'm going to have you turn in 1.4 and 2.2 tomorrow. Okay, so make sure you're done with those. And a reminder, tomorrow, it's not going to take the entire time to cover the section, so you might want to bring your book so you can work on it in class. Yeah. Accidentally left it.
Yep.
Thought you were going to say your parents took it to Arizona.
No.
Okay, so let's take a look at the next section. Again, it's on the back of the first page of that packet. So 2.2 is on graphs and symmetry. Yeah. Yeah. Were you here yesterday? Okay. Will you make sure did you sign the roll? Okay. Okay, so again, graphs and symmetry. When you first learned how to graph things, graph equations, you probably worked with lines, and the first thing you probably did is you made an XY table, you picked a bunch of X's, you plugged them in, and then you graphed them. Okay, that's the easiest way to graph something. It's not the most efficient. It's a lot better if we know some things like what the overall shape is and stuff like that. And we're going to talk about that in just a second. But this first part, there are lots of easy problems on this particular assignment. There are some that are a little bit more difficult, and we'll get to those toward the end. But we want to talk about a couple really important ideas. These are ideas that are very simple, that you all know. It's just that people tend to forget these. Okay? And if you can keep these straight, it's going to make things much better in the long run. So the first one is this. Again, building on that idea of you started off by making an XY table. You found a pair of points, an ordered pair that worked in the equation, and then you graphed it, and then you connected those points, maybe with a line or a curve or something like that. So if a point works in the equation, then it's on the graph. It's on the graph of that equation. But the opposite is also true. Sometimes we're not given an equation, we're given a graph. But we know something about that particular point on the graph. So if a point is on the graph, it works the other way too. If it's on the graph, then it works in the equation. So it's kind of a two-way street there. So you have some problems that are literally this simple. They take advantage of this two-part idea here. It says, determine if the given point is on the graph of the equation. And plug them in, it should make the equation true if it's actually on the graph. So we put a 1 here for the y. I'm going to put a 1 there and I'm going to cube that. Again, it looks a little bit silly cubing a 1 because we know what the answer is for that, but that's a good skill. Always plug things in parentheses. So this is 1 equals, this would be 1 minus 2. So that would be 1 equals negative 1. Does it work when we plug it into the equation? Nope. So it's not on the graph. Okay? I mean, it's literally that simple. Plug it in. If it works in the equation, then it's on the graph. If it doesn't, then there's no way it can be on the graph. So again, keeping with the idea that XY tables and plugging in points, that's, I mean, kind of nice to some extent, but not very efficient. It would be much better if we knew things like, what's the overall shape of the graph? Okay? Is it a parabola? Is it a line? Is it a cube function or something like that? Okay, and we're going to learn lots more types of equations and graphs in 1050, so you'll want to get used to that. Okay, and a lot of times we want to know what any of the other important features are. So things like intercepts. Intercepts are pretty darn important. We spend lots of time finding intercepts on graphs because they're usually pretty key features of the graph. So if you take a look at this next part right here, I've got 3 x-intercepts marked on here, and I've got 3 y-intercepts marked on here. So let's talk about the x-intercepts to start with. I've got this one here, and this one here. What do all of those have in common?
X-axis.
They're all on the x-axis, which is why we call them x-intercepts. Let's write down the coordinates. Okay, now I happen to put a little grid on here so we could tell where these are. This is at, let's see, 1, 2, 3, 4. This is at negative 5, 0. This one's at negative 1, 0, and this one's at 2, 0. What do they all have in common? They're all on the x-axis, that's true. They're all x-intercepts. 0 for the y-coordinate, okay? So 0 for y-coordinate. If it's on the x-axis, it's got to have 0 for a y-coordinate because you went right or left. You didn't go up or down. If you're going to stay on the x-axis, you can't go up or down, so the y-coordinate has to be 0. Okay? Well, let's take a look at the y-intercepts. So this one right here is at 0, 4. This one's at 0, 1. And this one's at 0, negative 3. What do they all have in common? 0 for x. Okay? So if you were in my 1010 class, then you probably heard me say this all the time, and I asked you to actually memorize this phrase. If somebody says, how do you find intercepts? You should think, well, here's what I do. I make a little XY table. I put in a 0 for x. Then I put in a 0 for y. Then I'm going to plug each one of those separately into the equation and solve for the x and the y intercepts. Okay, now what you want to remember is this. It's a little bit counterintuitive. So if I plug in a 0 for x, here's my little XY table. If I plug in a 0 for x, which intercept am I trying to find?
Y.
The y-intercept. If I plug in a 0 for y, I'm actually finding the x-intercept. Okay? So remember, plug in a 0 for x, that'll give you the y-intercept. And if you plug in a 0 for y, that'll give you the x-intercept. So we're going to zoom in on this problem right here. We're going to go ahead and do this one. You'll notice of these two problems, this one's pretty darn easy. You're already familiar with the linear equation. The other one's a little bit more difficult. So let's take a look at this one right here. If I want to find the y-intercept, well, gosh, this is in slope-intercept form, right? So you can look at it and you can tell what the y-intercept's going to be. But let's just verify that. This would be y equals, 2 times 0 minus 3, so y equals negative 3. So the y-intercept is negative 3. Okay, and normally we write the whole point. We say the y-intercept is 0, negative 3, 0, negative 3. And then if I find the x-intercept, I plug a 0 in for y. So that's going to be 0 equals 2x minus 3. And then I just solve for what x is. So I'm going to add 3 to both sides and then divide by 2. So this is going to be 3/2. So there's the x-intercept. It's a linear equation, so it's only going to cross in one place. Okay, any questions there? Okay, let's look at the next one. It's a little bit more difficult. So again, I'm going to make an XY table. I'm going to plug in a 0 for x. That's going to find the x-intercept, or excuse me, the y-intercept, and then I'm going to plug in a 0 for y. So if I plug this in right here, 0 for x, that means I get 0 minus y squared equals negative 9. Negative y squared equals negative 9. So y squared equals 9. So what does y equal? Plus or minus 3. When we put the square root in a problem, we have to account for the plus and the minus. It could have been positive or negative to begin with. So that means one of them is negative 3 and the other one is positive 3. So this actually has two y-intercepts. Okay? It's got 2 of them. Okay, now let's plug in a 0 for the y and figure out what the x-intercept is. That would be x minus 0 squared. So that's just x equals negative 9, right? So this would be negative 9, comma 0, and there's the x-intercept. Any questions? Sure? Okay. All right, let's take a look at the next part. So the next feature that we want to study in relation to this section is something called symmetry. You're probably familiar with symmetry. You've probably seen it before. We're going to be a little more precise in the way we talk about this. And we're going to talk about 3 different types of symmetry. So the first one is symmetry with the y-axis. Okay, symmetry with the y-axis. Okay, and this type of symmetry is often called reflective symmetry because the graph looks the same when we reflect or when it's reflected across the y-axis. And sometimes this is called line symmetry or fold symmetry because when you fold the graph along the y-axis, the right looks the same as the left. So you're already really familiar with a graph that has this type of symmetry. It's just a regular old parabola, parent graph for a parabola. So this one, if I plug in a 0, I get 0. The vertex is at the origin. If I go over 1 from the vertex, I go up 1 squared, go over 2, up 2 squared, back 1, up 1 squared, back 2, up 2 squared, so that's up 4. And then in 1010, we labeled these points, graphed the whole thing, made it look nice. So it looked something like this, and I'm going to label these 5 points. So this is 2, 4, this is 1, 1, 0, 0, negative 1, 1, and negative 2, 4. Now, with that graph drawn there, you can see the type of symmetry that we're talking about here. So if I were to fold this right along the y-axis, this side would lay right on top of this side or vice versa. Okay? If it's symmetric with the y-axis is like the middle of the graph and the right side looks just like the left side. Okay? Now, when we talk about mixing these the left and the right, what this means is it doesn't matter whether I go to the right 2, I get the same function value as if I went to the left 2. So I can go to positive 2, I get a function value of 4. I can go to negative 2, I still get a function value of 4. So it doesn't matter if I plug in a positive 2 or a negative 2, I still get a 4. What if I plug in a 3? I get a 9. Isn't that the same thing as if I plug in a negative 3? So it doesn't matter whether I go right or left, I still get the exact same function value. Okay, that's what we get when we have a graph that's symmetric with the y-axis. Now, we're going to kind of generalize this idea by writing down a quick little rule that's going to come in handy later. Okay, and that is if xy is on the graph, we can tell it's symmetric with the y-axis because x comma y, one of these changes signs. Which is it? The x. Okay, this whole idea that it doesn't matter whether you go to the right or the left, what it's saying is you can go to x and get y, or you can go to negative x and get y. It doesn't matter. Go either direction you want, you're going to get the same function value. Okay, any questions? Okay, this is the second type, and it's probably the least important, and we'll talk about why we don't use symmetry with the x-axis very often, but let's run through and take a look at a graph and talk about this type of symmetry. Again, this is a type of reflective symmetry or line symmetry or fold symmetry. And when we say it's symmetric with the x-axis, that means we can fold it along the x-axis And now we're not talking right and left. If you fold it along the x-axis, we've got to be talking not right and left, up and down, top and bottom, okay? So the top looks the same as the bottom. Top is going to look the same as the bottom. So we're going to take a look at a graph right here. We need to make this. Does anybody in here know what this looks like just off the top of their head? X equals y squared? A couple, 2 or 3 people? Okay, let's take a look. Let's plug in a 0 for x. So I've already figured out my x coordinate's going to be 0. What does y have to be? What's the only way x can be 0?
0.
Is if y is 0. Take this and solve it for y. Take the square root. You get y equals 0. So if you plug in a 0 for x, you get a 0 for y. So 0, 0 is on the graph. Remember, it makes the equation true, so it's got to be on the graph. Somebody want to pick another number that we could plug in for x?
2.
Let's plug in a 2. Oh, that's not going to be very nice, because watch what happens when I plug in a 2. If I plug in a 2, I get 2 equals y squared. So then I'd have to take the square root, so I get y equals plus or minus radical 2. That's a little bit nasty. Can anybody think of a better number to plug in, McKay?
4.
Let's plug in a 4, okay? If I plug in a 4, here's what I get. Take the square root, plus and minus 2. So if you plug in a 4, you get out a 2, and you get out a negative 2. So let's graph those. Over 4 and up 2, over 4 and down 2. So we get 2 of those. Let's do one more. I'll pick it. Let's plug in a 1. If you plug in a 1, you get 1 equals y squared. So if you take the square root, y equals plus or minus 1. So you've got these points. Is it okay if I write it like this? 1 comma plus or minus 1. So go over 1. You'd have to go up to 1 and down to negative 1. Okay. So somebody that raised their hand, what does this look like?
Just looks like the parabola just on the side.
Looks like a parabola pointed toward the side, right? So opens to the right here. Okay. Now let's label a couple of these points. Remember, this one was 4 comma 2. This is 4 comma negative 2. This is 1 comma 1. And this is 1 comma negative 1. And this is 0 comma 0. Okay. This graph is symmetric with the x-axis because if you fold it along the x-axis, the top looks the same as the bottom. And if we looked at the points, I've got the point 4, 2, and I've got the point 4, negative 2. So can I complete this little phrase right here? If xy is on the graph, then so is x negative y. Before the x coordinate changed, because we were trading right for left, now it's the y coordinate that changes sign because we're trading top for bottom. Okay? Now, can somebody tell me, especially based off this graph and what you know from 1010, why don't we worry about this type of symmetry very often? What's wrong with this graph? Jonah?
It's not a function.
Okay, not a function. And how can you tell it's not a function?
Line test.
Doesn't what? I hear some whispering. Doesn't pass
Vertical line test.
vertical line test. Okay, of the 3 types of symmetry we're going to talk about, symmetry with the x-axis is probably the least important because no function will pass, or no function will have that type of symmetry. Okay, and we questions. Okay, all right, let's take a look at symmetry with the origin. Okay, symmetry with the origin is called rotational symmetry, and in this case, the graph looks the same when it's rotated 180 degrees about the origin. So the way you could do this is you could put your pencil on the origin and spin the graph 180 degrees. If it looks exactly the same, that's symmetry with the origin. Okay? I've got a graph here that is symmetric with the origin. Okay? It's the cubing function. Okay? So let's take a look at that one. I'm going to make a little xy table. Let's pick a couple points and plug them in. I'm going to plug in a 0 for x. If you plug in a 0 for x, what's y got to be? What do you get when you cube 0? You get 0. Okay, so it still goes through the origin. That's good. Plug in a 1. What do you get when you cube 1? You get 1. Plug in a 2. What would you get? 8. 2 times 2 times 2 times 2 is 8. So this point is 1, 1. This point is 2, 8. And this point was 0, 0. What would happen if you plugged in a negative 1? What happens when you plug in a negative 1 and you cube it? You get a negative 1, right? Because there are 3 negatives. 3 negatives make a negative. And you get 3 1s, so it's still a 1 for the value. Okay, so we're at negative 1 comma negative 1. And what happens if you plug in a negative 2? You get negative 8. So negative 2, negative 8. So these 5 points are on the graph. Looks like that. Now, if you kind of covered this up over here and couldn't see that, does that kind of look like a parabola? Like the right side of a parabola? A little bit. It's a little steeper. It's a little steeper. Can somebody tell me why this goes down instead of going up like a parabola does? Why does a parabola go up? Why does squaring make it go up and cubing has this side going down? Zach?
Because whenever you square something, it has to be positive. But if you cube negative, it stays negative.
Yep, that's exactly right. When you square something, whether you go right or left, you're always going to end up with a positive. That's why both sides of a parabola go up. When you're cubing, it's different. When you cube a positive, you get a positive. That's why it stays here in quadrant 1. When you cube a negative, you still get a negative because you've got cubing 3. You've got 3 negatives. All these answers are going to be negative. Now, take a good look at this. If you put your pencil right here on the origin and turned your paper 180 degrees, would it look exactly the same? It would. And again, we can summarize, we can generalize that by making this little statement right here. If I know a point that's on the graph, I can tell you another one that's got to be on the graph. Now remember, what we did up here was, we said, hey, if 4, 2's on the graph and it's symmetric with the x-axis, got a point up here, swing it down here. It's the y-coordinate that's going to change that horizontally. Okay? If xy is on the graph, so for example, if 2, 8 is on the graph, what other point has to be on the graph if it's symmetric with the origin? Negative 2, negative 8. Or in general, if xy is on the graph, what other point has to be on the graph? Negative x, negative y. They both change. Okay? They both change. All right. Any questions there? Okay. That's the idea behind symmetry. At least for this particular section. We'll learn more about symmetry in chapter 3. But let's take a look at some problems from your assignment. Some of them are really easy. Let's take a look at example 4. It says plot the point and then plot the point that's symmetric with it with respect to the x-axis, the y-axis, and the origin. X-axis, y-axis, and the origin. So we're going to call this a sub x. That's going to be symmetric with the x-axis. A sub y is going to be symmetric with the y-axis, and a sub o is going to be symmetric with the origin. So we'll label where these are. So a is at 4, 3. So we're right here. A is 4, 3. Where would a sub x be? Where would the point be that's symmetric with the x-axis? X-axis is here. We're going to take this point and we're going to, it's on the top right now, flip it down on the bottom. So it's going to be straight down here. So it's easy to graph, and either using the rules or just by sight, which coordinate changed? Is it the x or the y?
Y.
The y. 4, negative 3. What if we took this point, again, start at this one, and made it symmetric with the y-axis? Swing it over here. We put the point right there. There's the one that's symmetric with the y-axis. Which coordinate do I change? the x, okay? Remember, it's a little bit counterintuitive. You change the opposite of the one that you're working with, okay? If it reflects about the x-axis, the y-coordinate changes. If it reflects about the y-axis, the x-coordinate changes. And where would it be if it's symmetric with the origin?
-4, -3.
Yeah, they both change, right? So it's over here. A -4, -3, that's symmetric with the origin. Okay, are there any questions? Okay, let's go ahead and do this one here. This is at 3, -2. So there's the original point. And if it were symmetric with the x-axis, which quadrant does it end up in? It's in the first one. It's right here. That's symmetric with the x-axis. What if this point were symmetric with the y-axis? It's over here, and I'll leave that for you to label. And where would it be if it were symmetric with the origin? It would be up here. Oops. Okay. Any questions? Pretty easy? Good. Okay, let's take a look at the next couple. You have some problems that are like this. Symmetry is really easy to tell if you've got a graph. Okay, and in just a minute we're going to change it so you don't have a graph, but you have some problems that are just like this. I'm not going to do all of these, okay, but let's just take a quick look. It says, find the intercepts, state symmetries if any. So let's find the x-intercepts and the y-intercepts. X-intercepts, there's one right here and one right here. So that would be -2, 0 and 2, 0. Y-intercept would be down here at 0, -3. And what type of symmetry or types of symmetry does this have? Does the right look the same as the left? If you fold it along the y-axis? Yep, so we've got y-axis symmetry. What about with the x-axis? Top look the same as the bottom? Nope. What if I put my pencil right here and spun it 180 degrees? Does it look the same? Nope. So those are the answers. There are the intercepts, and it only has y-axis symmetry. Okay? Okay, intercepts are easy enough, aren't they? You can tell those just by looking at it. Let's look at this one, and I'm just going to talk about this one. I'm not going to write it down. Any symmetries here? None, because the top doesn't look the same as the bottom. The right and left certainly don't look the same. And if I spun this 180 degrees, it would look like this. Okay? So there's no symmetry here. By the way, what type of graph is this?
Exponential.
It's an exponential graph. Okay? We'd only have these two intercepts. Okay. Is it symmetric with the y-axis? Does the right look the same as the left?
Yeah.
Yep. Symmetric with the x-axis? Does the top look the same as the bottom?
Yes.
Yep. And what if I put my pencil right here and turned it 180 degrees? It would still look the same, right? So x-axis, y-axis, and symmetry with the origin. Okay? All three. This only has one. What is it?
Origin.
Origin. Symmetric with the origin. Okay? All right. Any questions? Okay, go ahead and flip the page over then. You also have a few problems that give you a picture and then they say, hey, complete the rest of this graph if it were symmetric with whatever it happens to be. In this particular case, it says complete it if it's symmetric with the y-axis. Well, the y-axis is right here, so we'd fold it along that line. And if it were symmetric with enough? Okay, would you do part B, please? Do part B and label 2 points on the graph there that's symmetric with the origin. Symmetric with the origin. So you could do this by taking the graph and spinning it, or think about the rule. If it's symmetric with the origin, how do the coordinates change? If you know one point on the graph, you can produce another point on the graph by just changing the sign of the coordinates. You just have to remember which ones change. Okay. If this is symmetric with the origin, we're going to make this graph be symmetric with the origin. If 2, 2 is on the graph, what else has to be on the graph?
-2, -2.
They both change, right? Symmetry with the origin, they both change. So -2, -2 would. Okay? The graph looks like this. So this would be -2, -2. And the only other reasonable point to graph on this would be this one right here, which would be 0, -4. And take a look here. If 0, 4 is on the graph, well, if you change the sign of each one of those, if you made them both negative, if you wanted to think of it that way, well, 0 doesn't have a sign, so it's going to stay 0, and that's going to become a -4. So there's symmetry with the origin there. Any questions? Okay, good. Then we have 5 problems left. And here's the problem with these. You don't get a graph.
No.
It's easy to look at a graph like this or like these and just look at it for a couple seconds and say, oh, I know what type of symmetry that has. I'm comparing the left with the right or the top with the bottom, or I'm spinning it about the origin. So what we're going to do now is we're going to write down a couple of tests. Now, you don't have to write anything down here. You just need to think about this because they're all completed. There aren't even any blanks to fill in on this. Okay? Now, these are kind of the basis for some stuff that we're going to do in Chapter 3. And unfortunately, there's not really a shortcut. If you don't have a graph, you're really stuck at this point going through these little tests. So here's how it works. If we want to test for symmetry with the y-axis, remember, symmetry with the y-axis, the left is the same as the right. Doesn't matter whether you go to positive x or negative x. So we should be able to replace every x with a negative x, simplify, and we should get exactly the same thing we got before. Okay, I'll show you how that works in just a second. If we want symmetry with the x-axis, that means the y's changed. Top was the same as the bottom. So replace every y with a negative y, simplify, and it should look exactly the same as it did before. And if it was symmetric with the origin, remember they both changed. So we're going to replace x with a negative x, y with a negative y, simplify, and see if we end up with the exact same equation. Okay? All right, so I do want to point out, again, these are rules that we're going to use. We're going to tweak them a little bit in Chapter 3 because we talk about symmetry quite a bit. They are not exactly the same as the ones written in the textbook, but these are going to be better in the long run. Okay, so if you look at these rather than anything in the textbook, that would be great. Okay, so this is problem number 56. This is out of the textbook. It says, for the following problems, list the intercepts and test for symmetry. Okay, so for the time being, I'm going to do one of these where we find the intercepts, and then after that, we're just going to test for symmetry. Okay, so I'm going to make an xy table, plug in a 0 for x to find the y-intercept. So this would be y squared equals 9, which means y equals plus or minus 3. So one of them's 3 and the other one's -3. So there are the intercepts. The x-intercepts, right? What about the y-intercepts? Or sorry, what about the x-intercept? Plug in a 0 here. So we get x plus 9. Move that over, so we get x equals -9. So here are the y-intercepts, and here is the x-intercept. You have several problems where they ask you to find intercepts. Even if it's a nasty problem, still got to go through and do that. Any questions there? Okay, now let's deal with the interesting part. Okay, checking for symmetry. We don't know what this graph looks like. Maybe you have some idea. Later on in the semester, you're going to have a really good idea of what this looks like. But we want to check to see if this has any symmetry. So for y-axis, so we replace x with, with negative x. So this is going to be y squared equals negative x plus 9. Now, can I simplify that at all? No, can't simplify it at all. So let's compare this with the original equation. Is it exactly the same? No, it's not. So the answer here is no. It is not symmetric with the y-axis. Guaranteed it's not symmetric with the y-axis. For x-axis, I'm not going to write it, but we replace y with negative y. So wherever there's a y in here, I'm going to replace it with a negative y. So I'm going to do negative y squared equals x plus 9. Can I simplify this? I can. That's y squared equals x plus 9. Now let's compare this with the original. Is it exactly the same? It is. So the answer there is yes. Symmetric with the x-axis. Okay, and how do you check symmetry with the origin? Replace both of them with their negative equivalents. So this is going to be negative y squared, negative x, plus 9. So this is y squared, negative x, plus 9. And then I compare that with the original. Does it look exactly the same? Nope. So here are the intercepts. And the only type of symmetry that this would have is symmetry with the x-axis. That's it. Little tedious, isn't it? Okay. Not many ways to get around that. Okay. Again, we're not going to worry about symmetry with the x-axis very much, so we'll at least cut our work by a third. And in the next chapter, I'll show you a slightly different way to do that, but we'll have to wait till then. Okay, so you should be fine finding intercepts. So let's just check symmetry. Y-axis, y equals the cube root of negative x. Can you simplify that at all? Just a little bit. There's one thing you can do. We could think of this as, remember, with cube roots, you're looking for groups of 3. 3 negative ones. So this would be y equals negative, cube root of x. Is this exactly the same? Nope. X-axis. Replace y with negative y. Any simplifying you can do there? Nope. Is it the same as the original equation? Nope. So the answer is no. And then let's take a look at the last one. Symmetry with the origin. Put a negative y in place of y. Put a negative x in place of x. Can I simplify this?
Yes.
This I can, because that would be, if I divided, well, let's see, let me write it like this. This would be negative y, negative cube root of x. If there's a negative on both sides, what could I do?
Cancel.
Cancel them out or divide both sides by a negative, so I get y equals the cube root of x. So is that the same as the original one? That is a yes. So yes, symmetric with the origin. Okay? Any questions? Okay, let's look at this one. We'll just talk about it really quickly and then we'll finish these up. What would happen if I plugged in a negative x? What's the first thing I'd do to it here? It'll square it. So does that change it at all? No. So is it going to be symmetric with the y-axis? Yep. So y-axis symmetry. What happens if I plug in a negative y? It's going to be squared. So it's going to be the same thing. So it's going to be symmetric with the x-axis. And what happens if I replace both of them with a negative x and a negative y?
Same.
It's going to be the same. So this is symmetric with all three of them. Okay? Now, did you get that? Did I go too quick? Some of them are pretty nice. Okay? Some of them go really quickly. Okay, let's take a look at these last couple. Now, these are both rational equations. These tend to be a little bit more difficult. People tend to struggle with these, figuring out whether they're exactly the same or different or whatever it happens to be. Again, y-axis, plug in a negative x. Here's what I'd get when I simplify. X squared plus 9, negative 3x. Is it the same? Nope. X-axis. I mean, do I even need to write anything down for this? Because it's going to be negative y. I don't change anything over here, so there's no way it's going to be the same. So the answer there is no. And if I do the last one, origin, this is where people get tripped up. Again, these are rational expressions. These are fractions. People tend not to like these. Replace y with negative y. If I replace that with a negative x, I'm going to get an expression that I've seen before. So this is going to be negative y, x squared plus 9, negative 3x.
So, yes.
Is it the same?
Mm-hmm.
How can you tell?
Because you can cancel out the negatives.
Yeah, you can cancel out the negatives. If you multiplied both sides by a negative, that would turn this to a positive. And instead of putting the negative on the top like we normally do, remember you can make put the negative on a fraction out front, on the top or on the bottom. If I put it on the bottom, that would make two negatives, and then it would be exactly the same. So the answer there is yes, it does have symmetry with the origin. Okay, any questions? Okay, let's see if we can figure this one out by just kind of visually plugging things in. If I plug in a negative x, is it going to be exactly the same? Okay, the top's going to be negative x to the fifth. The bottom's going to be negative x to the third plus 1. Is that exactly the same?
Yes.
Could you cancel the negatives? Could you cancel the negatives?
No.
Nope. Because this is part of a factor, this is part of a term. Okay? If you wanted to try that, and again, this is why I picked these problems. Most people think you can cancel those out. If I take out, cube that. If I take out a negative so I can cancel them, that's what it would have to be. So the answer there is no. X-axis? No way, right? No way it's going to be the same, so the answer there is a no. And then the last one, origin, change the y, change the x, change the x, and again, those are negative because we cubed them. Is there any way that's going to be the same?
Nope.
No. So, any symmetry on that last one? Not a single one. Okay? No symmetry there. Okay. Again, in the next chapter, we're going to cut out one of the types of symmetry. Okay? Symmetry with the y-axis and the origin are important. For my class, please make sure you come tomorrow with 1.4 and 2.2 done. We'll hand that in. If you have questions, please come and see me. I will post this video on the internet probably within an hour, so if you need to watch that or need to come in and get some help, that'd be fine. Please bring your book tomorrow because I don't think it's going to take the whole time. You'll probably have some time to work in class. Okay? Have a great day. Thanks.